Hello everyone, my name is Ravindu Silva. I'm a PhD student at UC Santa Barbara. Today I'm presenting our work, the GuideEnricher, protecting the anonymity of Ethereum mixing service users with deep reinforcement learning. Let's say you are user A, you want to transfer some tokens to the user B over public blockchains like Ethereum. Once you finish your transaction and the transaction is committed to the blockchains, anyone who can access the blockchain can see your transaction, which allow any actor who want to cluster these kind of transactions, reveal the user identity up to a certain extent, which raising significant concern in the privacy. To answer these questions, over the time, different mixing services have been introduced to the public blockchains under different cryptographic protocols, such as Tornado Cash, Railgun, and Cyclone protocol. Let's have a look at the same above scenario, sending money from user A to user B over public blockchain, but this time using a mixing services. Instead of sending money directly, you deposit your money to the mixing services. In parallel to the depositing process, we create a node which we call non-interactive zero-knowledge proof, which will be saved in the later withdrawing step, providing as a proof that the mixing service owns your money. Once you've done your depositing process, you have to wait a certain amount of time, allowing more users to interact with the mixing service and create more transactions in between your transactions. After completing the waiting amount, you can provide this non-interactive zero-knowledge proof and the address you wanted to transfer the money to the contract. Upon the successful verification of your non-interactive zero-knowledge proof, contract will release your fund to the user B. Also note, previously one single transaction now being obfuscated into 3 transactions, removing the link between sender and recipient and introducing more confusion. Also note, most of these contracts do not allow you to do arbitrary withdrawal and deposits. They are fixed value. For example, ETH1, ETH10, ETH100. Let's say you want to deposit 112 tokens. It should be done as 2 deposit to 100, 2 deposit to 1 token repository, 1 deposit to 10 token repository, and 1 deposit to 100 token repository, or any denominator. As respect to the number of deposits you perform, you will have the nodes which will be used in the later stage to withdraw your money. Also note, all this cryptography behind these mixing services are yet not broken. They are very solid, and the implementations are reasonable, and all the transactions are valued to the same amount. In a perfect setting, building the sender and the recipient link is impossible. Yet, users are unknowingly perform certain actions which damage the pseudo-anonymity of the contract and the transaction itself. Let's say you are a user and use the same address to perform the deposits and the withdraw actions. Regardless of how it's obfuscated, you can see it clearly belongs to a single user. Also, what if you didn't wait a significant amount of time? As you can see, there's no sufficient transactions between your deposits and withdrawal, and it's so easy to link that this belongs to a certain single user. To address these things, initially developers of these mixing services come up with a certain set of instructions. We call it guidebook. This guidebook contains the instructions that you should follow while using the mixing services in order to keep your pseudo-anonymity. For this example, this guidebook mentions you should wait a significant amount of time after performing the deposits action before performing the withdrawal. Also, you should not reuse the address to invoke the same deposit withdraw function. Now, question arises, is this guidebook is complete? The answer is no. The guidebooks are incomplete. Users are still unknowingly performs actions that compromises their anonymity. The current state of the art to identify these kind of compromising activities are postmortem analyses. Basically, this happened right after the contract deployed, and the transaction happened, which means damage has been done. Therefore, we required a proactive method to discover this kind of anonymity compromising pattern beforehand the deployment of the contract. So we introduced the GuideEnricher, the proactive method to enrich guidebook using the deep reinforcement learning. So we create a simulation utilizing a deep reinforcement learning agent, which is evade agent here. Evade agent is tasked to perform certain tasks, such as transferring certain amount of token from set of wallets to another set of wallets using a mixing services while evading the detector. Detector is a rule-based system which monitors the evade agents and check whether evade agents violate the guidebook constructions or not. While evade agents come up with the strategies to evade the detector, we extract its evasion strategies, analyze and extract yet unknown anonymity compromising patterns, and enrich the guidebook. Let's have a look at the in-detail description of the system design. First, we create the reinforcement learning environment, simulating the basic functionality of the money flow of the Ethereum blockchain, such as transferring token, viewing, updating balance, registering contract, etc. Then we created the mixing service on top of the reinforcement learning environment, simulating the core mixing functionality of the mixing service that we wanted to simulate. Then we create the evader agent, which is a deep reinforcement learning agent which interacts with the reinforcement learning environment and transfer some money via the mixing services while evading the detector. Detector is a rule-based system which monitor the evader agents and check whether evader agents violate the guidebook instructions. Guidebook, as mentioned, it contains the rules that you should follow while using the mixing services. So initially, we create our guidebook using the initial instruction given by the mixing services developers and heuristics extracted from the existing literature. For example, address match, which means, and if we see an address used for both deposits and the withdrawal actions, it could be the same user. And the second, unique gas prices. If you see two distinct transactions under same gas price, which means it's the same single user. And the last one, the linked ETH addresses, which means if you see two distinct transactions that has transaction in between them outside the contract, it's still you can link as the same user. Let's have a look at the one single step of the evader agents, how it's learned so far. We defined our observation space using a 11 long feature vector, but for the simplicity, we shrink it down to a few important features. For example, by observing the previous action, previous peak address, current wallet balance, and the balance of the mixing contract, likewise, and the agent decide to perform an action. In here, agent is deciding to perform a withdrawal using the address 1, and is going to wait 11 transactions before performing its next action. Then the crowd create valid transactions, facilitating evader agent to exploring more states. Once the detector starts its process, he observes right now the evader agents try to perform withdrawal action using the address 1, which being used previously for the deposits, which match with the address matching rule in the guidebook, which result in giving a penalized reward -1. Likewise, agent receive the plus minus rewards and keep doing this process until it come up with the successful evasion strategies to bypass the detector successfully. So likewise, we conduct this experiment on different setups under different simulations. As you see in these results for the simulation, that agents try to transfer 9 tokens spread into 3 wallets to 247 empty wallets. As you've seen, it's all 3 setups like Tornado Cash Nova, and the Railgun, agent being converged to optimal and near optimal normalized rewards, which resulting the agent could successfully able to come up with evasion strategies to bypass the detector. And also, we utilize the PPO algorithm to train our agents, and we compare with other learning algorithms like A3C, A23 to make sure that proximal policy optimization algorithm is performed better as we picked. So once we train the agent, we combine the train and the testing episode, providing more diversity for our analysis, and we filter out the episodes that has evading rate below 90%. Then we cluster it using DB scans and K-means algorithms to prune out the evasion strategy and sample them to examine it further. Once we extract the evasion strategies, we manually analyze these evasion strategies and examine them. And if we could come up with interpretations to these strategies as yet unknown anonymity compromising patterns, we extracted them as anonymity compromising patterns in the future. So this is one of our rules that we could extract it. This is associated to the unique gas price, which means if I'm recalling what is unique gas price is, if you see a pair of deposit and withdrawal transaction with the same gas price, it belongs to the same user. In order to evade that, evader agents insert more deposit before performing a withdrawal actions, removing the one-to-one link and including one-to-many confusion. This kind of transaction can be possible in the future, especially if a user want to perform a high-frequent transaction and they don't want to wait. Also, they don't want to bet different gas prices. So we include this rule to our guidebook by enriching our guidebook. And finally, we found another transaction pattern which associated to the linked ETH addresses. Where, if you are recalling what is linked ETH addresses mean, if you see 2 distinct ETH addresses which has transaction outside the contract, it could be linkable. In this scenario, address A1 has been doing their transaction between A1 and A4, A5 outside the contract. In a scenario like this, the agent split the money in the A1 addresses into fresh addresses like A2, A3, and then use these fresh addresses to interact with the mixing services. And we extracted this pattern and enriched our guidebook iteratively. So our contributions, we designed and developed the GuideEnricher, a DRL-driven method that simulates user interaction with mixing services to facilitate guidebook construction. We evaluate the GuideEnricher on multiple mixing services and demonstrate that GuideEnricher can facilitate extracting anonymity compromising pattern without requiring significant human effort. Finally, we presented the usage of GuideEnricher in continuously enriching the guidebook by iteratively updating the rule-based detector and our evaders. We highly encourage you to go and read the paper for the in-detail implementations and the evaluation results. Also, our code is public. I'm happy to answer your questions.